Paradoxes that will break your mind. What if everything you believe about reality is wrong? What if the world, this solid, predictable world, is stitched together with contradictions that make no sense? You step into an elevator, and it always seems to go down. You flip a coin, but somehow your choice was already known. You look at a green apple, and it proves that ravens are black. You make a decision that erases the past. You teleport across the galaxy, but are you still you when you arrive? These aren't riddles. These are paradoxes, and they aren't just clever puzzles. They are cracks in the logic of our universe. In this video, we're diving headfirst into the strangest corners of space, time, identity, logic, consciousness, and causality. We'll meet an immortal version of you, a hotel with infinite rooms, a raven that vanishes into a question, and a decision so absurd it destroys free will. Every story you're about to hear is true, or at least logically sound. But by the end, you'll start to wonder, is truth even real? Can we ever know anything for certain? Or are we just characters in a puzzle we were never meant to solve? This isn't science fiction. This is what happens when logic turns against itself and asks questions the universe refuses to answer. So if you've ever wondered, can a time traveler erase their own birth? Can a ship be entirely replaced and still be the same ship? Can something exist and not exist at the same time? Can infinity be real? Can you be dead in one world, but alive in another? Then hold on, because what starts as a strange thought experiment might just leave you questioning your own reality. This is not a video, it's a paradox, and by the time it ends, you may not see the world the same way again. Let's begin. The bootstrap paradox. What happens when time loops break reality? It starts with a mystery. A man finds a sheet of music, beautiful, complex, and unknown to the world. He studies it for years, learns every note, and then he travels back in time. There, he meets a young Beethoven, hands him the music, and disappears. Beethoven plays it. People are stunned. He becomes a legend. The music spreads across centuries. And one day, that same man finds it again. But now, a question lingers in the silence. Who actually wrote the music? This is the bootstrap paradox. It's not just a sci-fi idea, it's a real paradox that haunts physicists and philosophers alike. It's a loop in time, where something seems to exist without ever being created. And it doesn't just apply to music. Let's say a scientist builds a time machine. Years later, she travels back and gives her younger self a copy of the blueprints. The younger version builds the same machine and one day repeats the loop, giving the plans to her past self again. But where did the blueprints come from? They weren't invented. They weren't discovered. They just exist, with no origin. The object, idea, or information becomes causeless, locked inside a time loop, never being created yet never destroyed. Now here's where it gets really strange. If something can exist without ever being made, what does that say about reality itself? About knowledge? About creativity? If a person learns something from the future and teaches it in the past, who was the first teacher? One of the most famous thought experiments involves a time traveler who idolizes Shakespeare. He wants to meet the man who wrote Hamlet. So he travels back, finds Shakespeare's house, but it's empty. No one home.
No manuscripts.
Nothing. So he panics. He writes down Hamlet from memory and publishes it himself in Shakespeare's name. Centuries pass. He grows up reading Hamlet just like he always did, until one day he travels back again to make sure Shakespeare becomes Shakespeare. But if he wrote the play, and Shakespeare never existed, then where did the play originally come from? The bootstrap paradox gets its name from the idea of pulling yourself up by your own bootstraps, a phrase that originally meant doing something impossible, just like these time loops, because logically, they shouldn't work. They violate what we understand about cause and effect. And yet, in the mathematics of time travel, they are possible. They don't break the laws of physics. They just bend our understanding of them. In Einstein's theory of general relativity, space and time can warp and curve. If they curve just right, they could create what's called a closed time-like curve. In theory, this allows for time travel to the past. Some solutions to Einstein's equations, like rotating black holes or wormholes, suggest that loops in time could exist in extreme conditions. But even if we could build a machine or find a cosmic shortcut, the paradox remains. Who wrote the music? Who built the time machine? Who imagined Hamlet? Some physicists argue that the paradox proves time travel to the past is impossible. Others say the universe might self-consistently correct itself. That even if information has no beginning, the loop is stable.
No contradictions.
Just a strange, eternal echo. But what if that echo includes us? What if some ideas, our greatest inventions, our deepest insights, aren't truly ours? What if somewhere, sometime, we are caught in a loop, writing down things we were only told by someone who read them in something we wrote? The bootstrap paradox isn't just a question about time. It's a question about reality. Can something come from nothing? Can knowledge exist without ever being discovered? Or is time itself just a story we're telling, one that, in the end, loops back to the beginning? We don't know. But maybe we've already been told the answer. Maybe we just haven't written it yet. So the question is, if you met your future self, would you recognize the ideas they give you? Or would you think they were Zeno's paradoxes? The ancient riddle that time still can't solve. He was just one man, a philosopher, a thinker, living over 2,000 years ago in ancient Greece. But what he left behind still haunts modern science. His name was Zeno of Elea, and he broke reality without ever touching it. It begins with something so simple, you almost miss the trap. A race. The swift-footed Achilles is chasing a slow-moving tortoise. Achilles gives the tortoise a small head start, confident he'll catch it in seconds. But Zeno says, wait, let's think about it. To catch the tortoise, Achilles first has to reach the point where the tortoise began. But by the time he gets there, the tortoise has moved a little farther. Now Achilles has to reach that next point. And again, the tortoise moves ahead. No matter how fast Achilles runs, there's always a new distance to cross. A smaller one, then an even smaller one. Forever. Zeno's question was chillingly simple. How can you ever reach something if you must complete an infinite number of steps to get there? This is known as the dichotomy paradox, and it gets worse. Zeno said, before you walk across a room, you have to get halfway there. Before that, a quarter. Before that, an eighth. Never ends. Infinity, he claimed, lives in every motion, every step, every second. And if motion means completing an infinite number of things, then how do we move at all? Modern physics and mathematics have tried to solve it. They say, sure, there are infinite steps, but each one is shorter than the last. Add them all together, 1/2 plus 1/4 plus 1/8 plus 1/16, and they get closer and closer to a limit, a final answer, one whole. It's called a convergent series, and in math it makes sense. But here's the problem. The math may work, but does reality? When you watch someone walk, you don't see infinite steps. You don't feel time dividing endlessly. You just move. So is motion real? Or is it just how our brain smooths out the impossible? Zeno's paradoxes don't stop at footsteps or turtles. He imagined an arrow frozen in mid-air. At any single instant, it's not moving. So if time is made of tiny instants, and the arrow isn't moving in any of them, how can it move at all? If time is a series of frozen moments, does motion actually exist? Or is it just a trick of perception? And here's the strange part. Zeno had no stopwatch.
No telescope. No calculator.
Yet he uncovered problems that modern science is still wrestling with. Because today, in quantum physics, time behaves strangely. Particles blink in and out of existence. At the smallest scales, motion gets fuzzy. And the smooth flow we experience might be an illusion. Even space and time, which we thought were continuous, might be quantized, broken into discrete chunks, like digital pixels on a screen. But if that's true, Zeno's ancient riddles aren't just philosophy. They're physics. The deeper you go, the more reality unravels. We move, we breathe, we run. But underneath it all might lie an impossible structure, where distance is infinite, time is fragmented, and movement is an illusion. So the next time you take a step, ask yourself, did I actually move forward? Or did I just cross an endless sea of nothing and pretend it was real? Zeno's paradoxes ask one question over and over again. Is the world continuous? Or is it built from something smaller? And what happens when you finally reach the unexpected hanging? The paradox that destroys logic itself. He sat alone in his cell. A death sentence had been passed. The judge looked him in the eye and said, "You will be hanged at noon, on one weekday next week. But the day of the hanging will come as a surprise. You won't know the day until the executioner knocks on your door." The prisoner blinked, then smiled, because he believed he had just found a way out of death. That night, in the flickering candlelight of his cell, he began to think. If they hang me on Friday, he reasoned, I'll know it on Thursday night, because by then Monday, Tuesday, Wednesday, and Thursday will have passed, and Friday is the only day left. It wouldn't be a surprise, so it can't be Friday. He crossed Friday off the list. But now, he thought, if Friday's out, Thursday becomes predictable too, because if I'm still alive by Wednesday night, and Friday is impossible, then Thursday must be the day. Which means Thursday's no surprise either. He crossed off Thursday, then Wednesday, then Tuesday, then Monday. By sunrise, he smiled again. I've done it, he whispered. They can't hang me. The logic won't allow it. Then, on Wednesday at noon, the executioner walked in, and the prisoner was hanged, and he was completely surprised. This is the paradox of the unexpected hanging. A riddle so disturbing, so logically twisted, that it has haunted philosophers, mathematicians, and logicians for decades. It looks like a puzzle, but it's more than that. It's a trap, a logic loop that turns certainty into confusion. The paradox goes like this. If someone tells you that something unexpected will happen by surprise, but you logically eliminate all possibilities, and then it still happens, what does that say about logic itself? Can reasoning break reality? Or is the flaw inside you? This paradox isn't just about hangings or surprise quizzes. It applies to how we predict the future, how we trust our own thoughts, and how we define what a surprise even is. Because here's the twist. The logic was flawless. The prisoner was right. If he followed it all the way, there should have been no day left. And yet he was wrong, because the logic only works if he survives to reason through it. But once the hanging happens, the logic collapses under its own weight. Some say the paradox exposes the limits of human prediction. Others argue it proves something deeper. That self-reference in logic leads to contradiction. It's the same kind of trap that makes computers crash. That gives us the liar paradox. This sentence is false. Or Russell's paradox in set theory. Is what happens when logic eats its own tail. The unexpected hanging has been used to question the foundations of mathematics, probability, and even artificial intelligence. Because what happens when a machine tries to predict an outcome, based on the assumption that it won't be able to predict it? What happens when we do? The real terror of this paradox is not that the prisoner was wrong. It's that he was right, until he wasn't. That logic brought him to the edge of survival. And then reality changed the rules. He believed his thoughts would save him. But the executioner didn't care about logic. Only the calendar. So here's the question. If you knew something was coming, but logic told you it couldn't, would you trust your mind or your gut? And deeper still, can we ever truly be surprised if we think hard enough? Or is every shock just a failure to see the loop coming? In a world built on logic, what happens when logic leads us straight? The Banach-Tarski paradox. How to turn one sphere into two. Imagine this. You take a ball, any ball, the size of a tennis ball, Now you cut it into pieces, not with a knife but mathematically. You rearrange those pieces, and suddenly you have two tennis balls. Same size, same mass, same shape. You've just doubled reality. Welcome to the Banach-Tarski paradox, the theorem that says you can make something from nothing. It begins in the world of pure mathematics. In 1924, two Polish mathematicians, Stefan Banach and Alfred Tarski, published a proof so bizarre, so unnatural, that even today it feels like a prank. They proved that, under the rules of set theory, you can take a solid 3D sphere, split it into a finite number of non-overlapping pieces, and reassemble those pieces into two identical copies of the original sphere. Same size, same volume, twice the matter. It's called a paradox. But technically, it's not wrong. It doesn't break math. It is math. It uses something called the axiom of choice, a rule in set theory that allows you to pick elements from an infinite number of sets, even if there's no pattern for how you pick them. It sounds innocent, but in the Banach-Tarski world, it becomes a magic wand. With it, you can pull infinity apart and put it back together in ways that feel physically impossible. So what's really going on? The key is this: the pieces you cut the ball into aren't like puzzle pieces. They're not even atoms. They're non-measurable sets, so bizarre, so scattered, that you can't assign them volume or shape in any traditional sense. They're more like clouds of untraceable dust, scattered through infinite space. You're not duplicating anything we could ever build. You're rearranging infinities. But here's where it gets creepy. If the math is correct, and it is, then under a certain kind of logic, matter can be doubled. Imagine if you could do this with gold, or energy, or people. And the only reason we can't do it in real life? Physics doesn't allow it. But math does. In the real world, atoms can't be split infinitely. Matter follows the laws of conservation. You can't just pull two planets out of one. But Banach-Tarski isn't about atoms. It's about the underlying rules that math plays by. And sometimes, those rules are very different from reality. Here's the deeper terror. If our universe is governed by math, and math allows something this strange, then how much of what we call impossible is just waiting to be rearranged? Because if one ball can become two, what else can be split, twisted, and copied in ways we haven't even imagined? What if our entire reality is just a Banach-Tarski construction waiting to collapse? Or worse, what if it already has? And we never know. The grandfather paradox. What happens if you kill the past? You build a time machine, and you do it for one reason: to go back. Back to the moment before you were born. Back to the day your grandfather was still young, still alive, still vulnerable. You find him, you pull the trigger, he dies. And in that instant, so should you, because without your grandfather, there's no father. And without your father, you were never born. But then, who pulled the trigger? This is the grandfather paradox. A simple time travel story that destroys reality. It sounds like a sci-fi plot, but it's a serious problem in theoretical physics and philosophy. Because if time travel into the past is possible, even in theory, then causality itself comes under attack. Causality is the idea that every effect has a cause, that the future depends on the past, that you exist because your parents existed. But the grandfather paradox flips that upside down. If you can go back and change the cause, you erase the effect. But then, if the effect is gone, how did it cause anything? It's a loop, contradiction, a universe trying to delete its own history. Some physicists say, time travel can't happen, period, because paradoxes like this would collapse the laws of nature. Others suggest the universe would somehow correct itself, that you might try to kill your grandfather, but fate, physics, or randomness would always get in the way. The gun jams. You miss. He survives. The timeline protects itself. But what if it doesn't? What if every decision you make in the past spawns an entirely new timeline? One where your grandfather dies, but your own timeline, the one you came from, still exists. You're not erasing yourself. You're just splitting. And suddenly, there isn't one universe. There are infinite universes, a multiverse of broken timelines, all branching from the moment you interfered. This idea isn't just science fiction. It's rooted in the many worlds interpretation of quantum mechanics, a real theory, backed by real physicists. It says that every possibility actually happens in a different universe. So maybe the grandfather paradox isn't a paradox at all. Maybe it's just a fork in the road. But here's the twist. If time travel creates new universes, then what happens to the original? And if you can enter a timeline, can you also trap someone in one? Could a future traveler come back and change your past without you even knowing it? Would you remember? Would you feel it? Or would your reality simply shift and you'd never even know you were rewritten? And here's where the paradox becomes terrifying. What if it already happened? What if this timeline, your timeline, wasn't the original? In a universe where the past can be broken, how do you ever know? The Ship of Theseus. Are you still you if everything changes? Imagine this. An ancient ship sits in the harbor, weathered, glorious, legendary. The very ship that once carried the hero Theseus through storms, battles, and myths. But the wood has rotted, so the sailors replace one plank, then another, then another. Years pass. Eventually, every single piece, every beam, every nail, every rope is replaced. It looks the same, feels the same, but not a single original part remains. So here's the question. Is it still Theseus's ship? This is the Ship of Theseus paradox, an ancient thought experiment first posed over 2,000 years ago, and still tearing apart minds today, because it asks something deceptively simple. If all the parts of something are replaced, is it still the same thing? Now take that question and turn it on yourself. You are made of cells, but your cells die. They're replaced constantly. In fact, almost every cell in your body gets replaced over time. Your bones regenerate, your skin renews, even parts of your brain change. So if your body is not the same as it once was, are you still the same person you were 10 years ago? What about 10 minutes ago? What about tomorrow? It gets weirder. What if someone collected all the old pieces of Theseus's ship and rebuilt it somewhere else? Now you have two ships, one with all the original parts, one with the newer ones that carried on the journey. Which is the real Ship of Theseus? The one that remembers the voyage? Or the one that's made from the original material? Which one holds the soul? Now let's go deeper. In neuroscience, this touches on a terrifying idea. If we could upload your mind, your memories, your personality into a machine, would that machine be you? Or just a copy? What if we slowly replaced your neurons with artificial ones, one at a time? You'd still feel like you, right? But after enough replacements, are you now something else? Philosophers have argued about this for centuries. Psychologists say identity is memory. Biologists say it's continuity. But no one agrees on where you really live. Is it in your brain, your story, your atoms? Or is the self just an illusion we tell ourselves to make sense of change? Think about relationships. You change. Your partner changes. Yet you say, we're still the same couple. But are you? If everything evolves, bodies, beliefs, values, emotions, what anchors identity? What stops you from becoming someone completely different, without even realizing it? And here's the paradox's cruelest twist. If you cling too tightly to what you were, you resist change. If you embrace change completely, you risk losing yourself. So tell me, if one day every part of you was different, your thoughts, your body, your memories, how would you know you were still you? Or worse, what if you... The liar paradox. This sentence will break your mind. This sentence is false. That's it. Just 6 words. But those 6 words have baffled logicians, philosophers, and mathematicians for over 2,000 years. Why? Because if the sentence is true, then it must be false. But if it's false, then it must be true. It's not a trick. It's not a joke. It's a sentence that cannot be true and cannot be false. It exists in a loop, contradiction, a glitch in logic itself. And once you understand it, you can never unsee it. This is the liar paradox. And it doesn't just mess with language, it messes with truth itself. The first person to write it down was a man named Epimenides, a Cretan philosopher, who said, "All Cretans are liars." But he was a Cretan, so if he's telling the truth, then he's a liar. But if he's lying, then some Cretans must tell the truth, which would include him. And suddenly, your brain starts folding in on itself. The paradox spread through history like a virus. Philosophers tried to solve it. Mathematicians tried to avoid it. Even modern computers and AI systems are haunted by it. Because the liar paradox isn't just wordplay, it's a flaw in how we define truth. Think about this. Truth and falsehood are the foundation of logic. Everything we know, math, science, reason, it all depends on the idea that something is either true or false. But what if some things are neither? Or worse, both? The moment you allow that possibility, logic breaks. In the 20th century, a man named Kurt Gödel used a version of the liar paradox to destroy the dream of perfect mathematics. He showed that even in the most perfect logical system, there are statements that can't be proved or disproved. They're true in a sense, but you can never reach them using logic. His discovery, called Gödel's incompleteness theorem, changed everything. It shattered the idea that math could explain all truths, all from a paradox that looks like a riddle. And here's the chilling part. Modern AI, algorithms, and even programming languages can crash if they encounter logical loops like this. The liar paradox is a bug in reality. A sentence that shouldn't exist, but does. A ghost in the machine of reason. Now take this thought one step further. What if a person lied like this? Imagine someone says, "Everything I say is a lie." How do you trust them? How do you know anything they say? What if reality itself whispered that sentence to you? What if the universe said, "This existence is false"? Would you believe it? Or would believing it make it true? If truth depends on language, and language can contradict itself, how can we ever know what's real? And if even logic can lie to us, what else might be? Quantum immortality. What if you never die? Imagine this. You're standing in front of a loaded gun. It's aimed directly at your head. A scientist counts down. 3, 2, 1. The trigger is pulled. You should be dead. But you're not. The world flickers. And somehow you're still alive. Inexplicably. Unharmed. Everything feels off. And then, it happens again. The gun fires. But death never comes. Over and over. As if the universe is bending to keep you alive. This isn't a sci-fi story. It's a real theory. It's called the quantum immortality paradox. And if it's true, you will never die. Let's rewind. In the strange world of quantum mechanics, particles exist in superpositions, multiple states at once. They don't decide what they are until they're observed. This is the world of Schrödinger's cat, where a cat in a box is both alive and dead, until someone looks. Now imagine this concept applied to you. In 1957, physicist Hugh Everett III proposed something radical. Every time a quantum event could have multiple outcomes, the universe splits. One version plays out here, another version somewhere else. This idea became known as the many worlds interpretation of quantum mechanics. Now here's where it gets terrifyingly personal. Imagine you're in a situation where you could die. A plane crash, a heart attack, a coin flip deciding life or death. In some universes, you die, but in others, you survive. From your perspective, your consciousness, you only experience the versions where you live. Because in the worlds where you die, you no longer exist to notice. So subjectively, you never die. Every time death comes close, you skip to the universe where it didn't happen. To you, reality continues like nothing happened at all. But to everyone else, you're gone. Think about that. What if there are countless versions of you? Some who died young, some who lived to be 100, but you can only ever experience the path where you survive. Sounds like a gift. Immortality. But here's the catch. Over infinite time, Everyone you love would disappear. You'd outlive friends, family, entire civilizations. Eventually, maybe even the universe itself. You'd be the last flicker of consciousness, drifting through decaying realities. Alive, alone, forever. Some physicists say this is just a philosophical fantasy, an artifact of taking quantum theory too far. Others believe it's a logical extension of the math. They argue, if many worlds is real, then quantum immortality is inevitable. But here's what's truly terrifying. You wouldn't even know it was happening. From your perspective, you'd just be lucky. You'd brush off a car crash, recover from a disease that should have killed you, survive the impossible over and over again, never questioning why. And maybe, just maybe, that's already happened. Maybe the reason you are hearing this is because every other version of you didn't. And this universe, right now, is the one that let you live. So if death is never something you experience, can you ever truly die? Or are you already trapped in an endless chain of survival? With the omnipotence paradox, can an all-powerful being defeat itself? Can an all-powerful being create a rock so heavy that even it cannot lift it? That's not just a clever riddle. It's a weapon. A quiet, elegant riddle that tears open logic and bleeds meaning from the word omnipotence itself. Because no matter how you answer it, yes or no, the result is the same. The being is not all-powerful. Let's slow down. If the answer is yes, it can create the rock, then there's something it cannot do, lift it. And if the answer is no, it can't create the rock, then there's something it cannot do, create it. In both cases, there's a limit, a boundary, which means omnipotence breaks. This is the omnipotence paradox. It doesn't just ask if a god or force can do anything. It asks if the very concept of infinite power is even coherent. Because if a being is truly limitless, can it limit itself? Can it destroy itself? Can it cease to be? Some have tried to fix the paradox with clever language. Philosophers say, omnipotence means being able to do anything that's logically possible. In other words, a square circle? A married bachelor? Nonsense. You don't blame a being for not doing the impossible, they argue. Just like you don't blame a painter for not drawing a sound. But others push back. Isn't the whole point of omnipotence that no limits apply? Shouldn't infinite power include even the power to break logic? Or else, it's not truly infinite. Theologians have wrestled with this for centuries. If a god is all-powerful, all-knowing, and perfectly good, why does evil exist? Why suffering? Why death? Is it because even infinite power has rules? Or is the paradox a sign that we don't really understand what we're asking for when we talk about gods and infinity? Now zoom out. This paradox isn't just about religion. It's about us. Our dreams of absolute control. Our fantasies of building an unstoppable AI. A machine that can do anything. Everything. But what happens when that machine meets this question? Can it override itself? Rewrite its own code? Delete its own existence? And if it can't, is it really all-powerful? The omnipotence paradox doesn't offer answers. It offers a mirror. And the more you look into it, the less sense power seems to make. Maybe some things can't exist. Not because they're too big or too strange, but because they're too perfect. So perfect, they collapse under their own weight. So ask yourself, if nothing is beyond the power of an all-powerful being, can it make itself not all-powerful? And if it can, what survives? The Sorites paradox. When does a heap stop being a heap? How many grains of sand make a heap? 10? 100? 1,000? Okay, now let's say you have a heap, just a normal pile of sand, and you remove one grain. Is it still a heap? Probably yes. So you remove another. Still a heap. And another, and another, and another, until you're down to one last grain. Is that still a heap? No? Then where exactly did it stop being a heap? Which grain was the magical grain, the one that erased its identity? This is the Sorites paradox. And it's not really about sand. It's about language, categories, and how vague boundaries can quietly destroy logic. The word sorites comes from the Greek soros, meaning heap. This paradox has haunted philosophers since ancient times. Why? Because it shows something deeply unsettling. Our world is built on vague concepts, and those concepts don't always hold up under scrutiny. Here's another example. When does a person go bald? Is it 10 hairs? 100? 1,000? What if you pluck one hair at a time? At no point is that person suddenly bald, but somehow they become bald. So when exactly did the change happen? There's no clear line, no definite moment, and yet something changed. And the same applies to so many things we assume are obvious. When does a child become an adult? When does a hill become a mountain? When does a crowd become a mob? When does a lie become a betrayal? There's no sharp edge, just a slow, creeping fog of change. And we're forced to draw arbitrary lines in that fog, hoping no one questions them too hard. This is where the paradox gets dangerous, because vague language isn't just a curiosity. It shapes laws, identity, justice. At what point is someone legally intoxicated? How poor do you have to be to qualify for help? How sick is sick enough? How dangerous is too dangerous? The answers depend on definitions. Definitions we pretend are solid. But the Sorites paradox whispers, they're not. So what do? Some philosophers argue that the problem lies in language, not reality. That concepts like heap or bald are fuzzy by nature. Others try to fix it with mathematics, using probability or degrees of truth instead of binary logic. Still others say maybe there is no problem. Maybe we just need to live with the fuzziness. Embrace the gray. But then, how do we ever make clear decisions in a blurry world? If removing one grain of sand doesn't destroy a heap, then what else in your life, your identity, your beliefs, your truth, is quietly changing one grain at a time, without you ever knowing? Russell's paradox. The set that destroys itself. What happens when logic eats itself? This is a story about a question so dangerous, so quietly explosive, that it broke mathematics. It starts with a simple idea. Imagine a set, a group, a collection, like a set of shoes, or a set of rules, or a set of all cats in the world. Now imagine a different kind of set. A set that contains only sets that do not contain themselves. Strange? It gets worse. Because once you imagine that, you're forced to ask one deadly question. Does this set contain itself? If it does contain itself, then by definition it shouldn't. But if it doesn't contain itself, then by definition it should. Either way, you're stuck. A logical loop with no escape. And that, right there, is Russell's paradox. In 1901, British philosopher and logician Bertrand Russell stumbled into this problem while writing to Gottlob Frege, one of the founding fathers of modern logic. Frege was just about to publish his life's work, an airtight system that would define all of mathematics using pure logic and set theory. Russell's letter ruined everything. His paradox exposed a hole, a silent bomb hidden in the foundation of math itself. Because if you could define a set of all sets that do not contain themselves, and then couldn't logically say whether it contains itself or not, then the whole system falls apart. Frege was devastated. In his own words, Russell's paradox shattered the foundation of his work. And Russell wasn't just poking holes. He was warning the world, our understanding of logic is incomplete. But let's leave the math classroom for a moment. Let's think about this paradox like a story. Imagine a village barber. This barber shaves everyone in the village who does not shave themselves. So here's the puzzle. Does the barber shave himself? If he does, then he must not, because he only shaves those who don't. If he doesn't, then he must, because he shaves everyone who doesn't. That's Russell's paradox, tucked into a barber's dilemma. This kind of contradiction isn't just annoying, it's fatal to logical systems. Because once you allow a contradiction to exist, anything becomes provable. Any conclusion, no matter how absurd. That's why this paradox set off a revolution in mathematics. To fix it, mathematicians developed new systems like Zermelo-Fraenkel set theory, which placed strict rules on how sets can be formed. No more wild, unrestricted sets of all sets. No more barbers who shave everyone but themselves. Russell himself even tried to fix it with his theory of types, layering sets into hierarchies to prevent self-reference. But the damage was done. The dream of building all of math from one clean, perfect logical foundation was dead. Russell's paradox wasn't just a problem to be solved. It was a mirror, a glimpse into the limits of human thought, that even the most basic concepts like a set can hide infinite traps. That reason, no matter how sharp, can fold in on itself. And that sometimes the very act of asking a question is enough to break the universe you're building. So ask yourself, if a set that contains itself is a paradox, what else in your world, your identity, your mind, might be built on a loop you haven't noticed? The observer's paradox. The truth disappears when you look at it. What if just by looking at something, you change it so much that you can never know what it really was? This is the observer's paradox. A quiet, invisible force. One that ruins our ability to ever truly understand anything. And here's where the nightmare begins. Every time you try to observe reality, you distort it. Every time you try to measure behavior, you influence it. Every time you try to find the truth, you push it further away. Let's start small. A linguist walks into a village. She wants to study how the locals speak naturally. So she pulls out her notebook, starts recording conversations. But now, the villagers are aware they're being watched. So they speak differently, more carefully, more formally. They're not lying, but they're not being themselves anymore. The pure, raw truth she came to observe, it vanishes. That's the observer's paradox. It's not just about language. This paradox appears everywhere. In classrooms where students behave better when they know they're being graded. In police interrogations where suspects speak differently when a camera is on. In medicine, where patients show better results just because they think they're being studied. And in quantum physics, where it becomes downright terrifying. Picture a single particle, a tiny speck of reality, a quantum traveler. It exists in multiple states until you observe it. And the moment you measure it, collapses, picks one version of itself, one position, one reality. Your observation forced it to choose. This is the famous double-slit experiment. When you don't observe the particle, it acts like a wave, spreading out, existing everywhere at once. But when you observe it, it behaves like a particle, choosing a path, becoming definite. Reality changes, depending on whether or not you're watching. Think about that. Something as simple as watching can tear the fabric of reality into two different versions. Which one is true? And more importantly, is there ever such a thing as truth when it can't exist without distortion? This paradox doesn't just haunt science. It haunts us personally. We behave differently when we know we're being watched. On social media, in relationships, at work, even alone. Our inner lives shift under the weight of someone else's gaze. Are you really being yourself? If someone's watching, are your memories real? If you can't stop narrating them for someone else? So we try to build better tools. More hidden microphones. More discrete cameras. More neutral experiments. But no matter how small we make our footprint, the act of observation is never truly passive. We leave fingerprints on everything we study, even truth. So here's the question that may never have an answer. Is it possible to observe anything at all without changing it? Or will the truth always slip away? The moment you look, the unexpected lottery paradox. Why you'll never win until you do. What if I told you you're gonna win the lottery? Not someday, not maybe, but this week. You're told, you will win the lottery this week, but the day it happens will be a complete surprise. You smile, you dream, you imagine waking up to the impossible. But then you start thinking, really thinking, and what happens next destroys your belief before the week even begins. Here's how the mind trap unfolds. You reason, well, it can't happen on Friday, because if I make it to Thursday night without winning, then I'll know it's coming Friday, and that would ruin the surprise. So Friday is out. But now, Thursday is no longer possible either, because if I get to Wednesday night and haven't won yet, and I've already ruled out Friday, then Thursday becomes predictable too. So Thursday's gone. Now the same logic eliminates Wednesday, then Tuesday, and suddenly, you've reasoned yourself out of ever being surprised. You go to bed Sunday night absolutely convinced. This lottery win? It can't happen. But then Monday morning arrives, and you win. You're shocked. You stare at the numbers. You stare at yourself. You were certain it couldn't happen, yet here it is. This is the unexpected lottery paradox. A logical loop where knowing too much destroys what's meant to be unknowable. It's based on a cousin paradox, the unexpected hanging, where a prisoner is told he'll be executed unexpectedly next week. Yet the same kind of reasoning spirals into contradiction. In both stories, something strange happens. The person involved uses logic to eliminate the very thing that was going to happen, and then reality ignores their logic. So, where did they go wrong? Was it in assuming they could predict a surprise? In trusting their own reasoning? Or was the flaw deeper, hidden in how humans understand time and expectation? Some philosophers say this paradox exposes a crack in our understanding of belief itself. Others say it reveals how logic and uncertainty can't always live in the same room. You can't fully prepare for a surprise without killing it, and yet the surprise still arrives. It's not just about hangings or lotteries. This paradox lives quietly in your everyday life. You plan for the unexpected. You try to predict the unpredictable. But does that mean it won't happen? Or does it mean you just won't see it coming? So here's the paradox you'll carry with you. Can you truly prepare for the unexpected without destroying it? Or is surprise the one thing that only exists when you stop trying to understand? The twin paradox. What if your brother came back younger than you? Imagine this. You and your twin are born at the exact same moment. You grow up together, laugh together, fight, dream, wonder, until one day your twin boards a spaceship. Not just any ship, but one capable of near-light speed. They wave goodbye and vanish into the stars. You stay behind. You live your life. You age. You wait. And then, years later, their ship returns. The door opens. You rush forward. And standing there is your twin. But something's wrong. They're younger than you. Noticeably younger. Still full of youth. While you've grown old. You were born together, but now you live in different times. How is that possible? This is the twin paradox, a strange consequence of Einstein's theory of relativity. At first glance, it feels impossible. If time flows equally for everyone, how can two twins experience different amounts of it? But here's the twist. Time doesn't flow equally for everyone. Einstein's special relativity tells us something bizarre. The faster you move through space, the slower you move through time. So when your twin raced across the galaxy at near light speed, their experience of time slowed down. Not because their clock broke, not because of a trick, but because this is how time actually works. Time is relative. From their point of view, only a few years passed. But for you, decades slipped by. You were both right, and yet you ended up years apart. But wait, shouldn't each twin see the other as moving? Shouldn't both of them think the other aged slower? Here's where the paradox really stings. Only one twin turned around. Only one changed direction. Only one experienced acceleration, breaking the symmetry. And that tiny difference changed everything. It wasn't just speed. It was motion plus change in motion. That's the hidden key. And the moment they turned back toward home, their clock began ticking at a different rhythm. Sounds like science fiction, but it's been tested over and over. We've flown atomic clocks around the Earth on planes, and watched time slow down just a little. Astronauts aboard the ISS age slightly slower than the people on Earth, by mere milliseconds. It's real. The universe bends time in ways we can barely grasp. Now ask yourself, if time isn't fixed, if it stretches and shrinks depending on speed and gravity, what else is flexible? Is now even the same for you as it is for someone across the galaxy? Is the past truly behind us, or could it still exist somewhere, frozen in someone else's frame of reference? So here's the paradox that haunts every ticking clock. If time is relative, then what does now even mean? And if your twin can come home younger than you, what else can time do that we haven't? The teletransportation paradox. What if you died and didn't even notice? Imagine this. You step into a sleek chamber. You're calm, confident. You've done this before. The technician smiles. The countdown begins. You close your eyes as a voice says, "Ready for teleportation in 3, 2, 1. Then silence. And then, you open your eyes. You're on Mars. You look down. Same body, same thoughts, same memories. You're you. Or are you? This is the teletransportation paradox. It begins with a simple idea. What if we could build a machine that scans every single atom in your body, destroys the original, and then reconstructs you atom by atom in another location? You wouldn't feel pain. You wouldn't notice a gap. It would feel like waking up from a nap. But there's a catch. You were disintegrated. The original you was vaporized. And what stands in your place is a perfect copy. Now here's the question that splits philosophers down the middle. Did you just travel to Mars? Or did you die, and a duplicate took your place? Some argue, if the person on Mars has your memories, your personality, your exact body, then what's the difference? They laugh like you, cry like you, love like you, they believe they're you. And maybe that's all identity ever was, a pattern, a continuity. But others say, no, the moment your original body was destroyed, you died. The new version may think it's you, but it's not. It's a copy. No matter how perfect, copy is still a copy. And here's where things get even darker. What if the machine didn't destroy the original? What if it created the copy, and the original stepped out fully intact? Now, there are two of you. Each one believes they are the real you. Same memories, same goals, same soul if you believe in that. So, who gets to live your life? Who owns your name, your friends, your identity? Which one is the real you? And what happens to the other? Do we call them an imposter? Or worse, a mistake? The paradox forces us to ask, what are we really? Are we a soul tied to a specific body? Or are we just patterns of thought, running on a biological machine? If it's the pattern that matters, then teleportation is just fine. If it's the continuity of experience that matters, then teleportation is death in disguise. This isn't just science fiction. In a world where brain scans, mind uploads, and AI simulations become more real every year, this question is coming for us. One day, you may be offered the chance to live forever, to upload yourself, to escape death. But the question won't be, can you survive the process? It'll be, will it still be you who wakes up? So ask yourself, if a perfect copy of you stood in front of a mirror, would they see you? Or would they be someone else, pretending not to know? The Sleeping Beauty paradox. When time breaks your mind. Imagine this. You lie down on a bed. A voice speaks softly. We're going to put you to sleep now. Just relax. And then darkness. You wake up. A quiet room. No clock. No window. You don't know what day it is. But you remember the experiment. They told you something strange would happen. You would be put to sleep on Sunday. Then a coin would be flipped. If it landed heads, they'd wake you up on Monday, only ask you one question, and the experiment would end. If it landed tails, they'd wake you up on Monday and again on Tuesday, but erase your memory after each waking. So every time you wake up, you won't know what day it is. You won't know whether this is your first awakening or your second. Now here's the puzzle. You wake up. You're sitting there, groggy, unsure if it's Monday or Tuesday. You remember the rules, and then they ask you one simple question. What is the probability that the coin landed heads? First, you might think, well, the coin flip was fair. It's 50-50, heads or tails. But then your mind starts racing. Wait, if it landed heads, I would only be awakened once. If it landed tails, I would be awakened twice, but with no memory of the first. So there are more total awakenings in the tails world than in the heads world. Statistically speaking, if I'm awake right now, isn't it more likely that I'm in one of the two tails awakenings? Shouldn't that make the chance of tails 2/3? And just like that, your reality breaks in two. Philosophers and scientists have argued for decades over this exact problem. Some say the probability should be 1/2 because the coin itself was fair and you're just updating information. Others argue it's 1/3 for heads and 2/3 for tails because you're more likely to find yourself awake in the tails scenario since it has two chances. Both answers seem logical. Both answers feel wrong. But here's the real question this paradox forces us to ask. What does it mean to be you at a specific moment in time? When your memory is unreliable, when time is uncertain, when multiple versions of you might exist without knowing it, can you even trust your own experience? It gets worse. This isn't just about coin flips or fairy tales. It connects to real debates in consciousness, artificial intelligence, and even cosmology. If the universe is infinite, and infinite versions of you exist, waking up in infinite rooms, then how do you ever know which one you are? And maybe that's the real paradox. Not the coin, not the math, but the terrifying thought that even right now, you might be in the middle of something you don't remember entering, with rules you don't fully understand, just trying to guess based on the fact that you woke up. So ask yourself, if you can't trust your memory, can you ever trust the moment you're living in? And more hauntingly, are you the first version of yourself to wake up today, or just the one who still thinks? The infinite hotel paradox, where no room is ever full.
Imagine a hotel.
Not just any hotel. This one stretches forever. Endless hallways, endless rooms, and every room already has a guest. There's no end. It goes on and on and on. This is Hilbert's hotel, a thought experiment dreamed up by mathematician David Hilbert. A place so strange it could only exist in the world of infinity. Now picture this. A man walks into the lobby. He says, "I need a room." The manager smiles. "But we're full," he says. "Every room already has a guest." And then he adds, "But don't worry, we still have space." Wait, what? Here's what the manager does. He calls every guest and says, "Please move to the next room." Room 1 moves to room 2. Room 2 moves to room 3. Room 3 to room 4. And so on. Forever. Now room 1 is empty. The new guest walks in. Problem solved. Even though the hotel was completely full, it still made space for one more. This is infinity's first trick. Full doesn't mean full. Infinity can always stretch. Just a little more. But things get weirder. Now imagine a bus pulls up. With an infinite number of new guests. The hotel manager shrugs. "No problem." He tells every current guest, "Go to the room that is double your current number." Room 1 goes to room 2. Room 2 goes to room 4. Room 3 to room 6. Now all the odd-numbered rooms are empty. And that's an infinite number of rooms. The infinite busload of people moves right in. Every single one gets a room. No one is left out. But wait, there's more. A second bus arrives. Then a third. Then 1,000. Then infinite buses. Each with infinite guests. Can the hotel still make room? The answer is yes. Mathematically, the manager can still rearrange everyone to make space. It's confusing. It's absurd. But it's real. Infinity isn't a number. It's a process. This paradox isn't just about hotels. It reveals a terrifying truth. Our human logic breaks down when we try to grasp the infinite. In an infinite universe, the impossible becomes possible. You can always add more, subtract everything, and still be left with infinity. Things that make perfect sense in our world collapse when stretched across endless time or space. Physicists think our universe might actually be infinite. If so, then somewhere out there may be infinite copies of you. A version of Earth where you're watching this video again, and another where you're not. But here's the question that keeps mathematicians and philosophers awake at night. If infinity behaves like this, does anything we do actually matter? If everything happens somewhere, if there's always more space, more versions, more outcomes, what does that make you? Are you special? Or just one guest, in one room, in a hotel with no end? So ask yourself, if you checked into Hilbert's hotel tonight, would you ever know which version of you actually walked in? Or are you already in the hotel, still waiting for the moment you realize you never the measure problem? Why you might not exist, statistically. Imagine this. You open your eyes. You breathe. You're alive. You think, this is real. But what if I told you that in the vast structure of the universe, you might not even matter enough to count? This is not a riddle. It's a real problem. It's called the measure problem, and it's one of the most disturbing paradoxes in modern cosmology. Because if the universe is infinite, then everything that can happen does happen. Not just once, but an infinite number of times. There are infinite Earths, infinite yous, infinite copies of this very moment. Now ask yourself, how do you calculate probabilities in a world where everything happens somewhere infinitely? Let's say a physicist wants to answer a simple question. What's the chance that the next planet we discover has intelligent life? Easy, right? You count the number of Earth-like planets with life. Divide by the total number of Earth-like planets. Simple math. But here's the catch. If the universe is infinite, then there are infinite planets with life, and infinite without. Infinity divided by infinity is not a number. It's undefined. You can't calculate a probability. You can't say what's likely. You can't even say what's typical. So cosmologists try to work around. They invented measures, ways to cut off infinity, to limit the sample, to make calculations possible. But here's where it gets weird. Different measures give different answers. Depending on where you cut the data, you might predict a universe that's cold and empty, or one that's dense and fiery. A universe where intelligent life is rare, or one where it's everywhere. A universe where you should exist, or one where your consciousness is deeply improbable. Now imagine you try to define a typical observer in this cosmic sea. You ask, what kind of being is most likely to exist in this universe? And some measures say, Boltzmann brains. Tiny, random fluctuations in empty space that spontaneously form for a brief moment, with fake memories, fake thoughts, and then vanish. Statistically, they say, you shouldn't exist as a human on Earth. You should be a brain, floating alone in space, imagining all of this, just a random blip, in an ocean of chaos. Of course, that feels wrong. You feel real. You have a body, a life, past. But the math doesn't care about feelings. And in an infinite universe, normal might not mean what you think. This is the heart of the measure problem. When everything happens somewhere, and happens infinitely, how do you define you? How do you even define truth? Are we rare? Are we typical? Or are we just an illusion, trapped inside statistics that don't know how to stop counting? Even worse, every theory of the universe that includes inflation, or a multiverse, or quantum randomness, runs into this wall. A wall where answers depend more on how you count than what is real. So ask yourself, if you are one of infinite versions of yourself, how do you know this one is the one that matters? And in a universe that refuses to give you a solid answer, are you calculating reality or just get the two envelopes paradox? Should you switch? Imagine this. You're sitting at a table. Across from you is a sealed envelope. Next to it, another one. You're told one envelope has twice as much money as the other. You pick one, say the one on the left. You open it. Inside is $100. Now comes the question, do you want to switch? You hesitate. The other envelope could have $50, or it could have $200. But the longer you think about it, the more your brain starts to loop. Let's do the math. If the other envelope is equally likely to have $50 or $200, then your expected value is
Een half maal $50 plus een half maal $200 is gelijk aan $25 plus $100 is gelijk aan $125.
That's more than your $100. So you should switch, right? But wait, now imagine you do switch. You open the second envelope. It has $200. Now you think, hold on. Maybe the first one had $100? Now the other envelope might have $100 or $400. So the expected value is now
Een half maal $100 plus een half maal $400 is gelijk aan $50 plus $200 is gelijk aan $250.
So you should switch again? But that leads to a loop. No matter which envelope you open, you always think the other one is better. Forever. And now you're trapped. This is the two envelopes paradox. A perfect mathematical illusion. Feels like you should always switch. But if that were true, you'd never stop switching. Back and forth. Again and again. And logically, that doesn't make sense. Something's wrong. So what's the catch? The paradox hides its trick in probability. You assumed the other envelope has a 50/50th chance of being higher or lower, but that only works if there's a fixed starting point. In reality, one envelope must have started the process. There's a base amount of money that determines the rest. If you start with $100, the other envelope is either $50 or $200. Yes, but if $100 was already the larger amount, then there's no way the other envelope has $200. Your expectations are off. You're calculating averages, based on impossible scenarios, and that's where the paradox lives. It tricks your brain by using your own reasoning against you. The very logic that should help you decide is the thing that traps you, and it gets even deeper. What if you don't open the envelope at all? What if you don't even know how much is inside? Even then, some versions of this paradox say, you should still switch. Why? Because no matter what, you might gain more. But that makes no sense. You have no data, no baseline, no reason. And yet the math whispers, switch, switch, switch. Now think bigger. What if this isn't about envelopes? What if this is about life decisions, jobs, relationships, futures, the endless belief that the other option is better? Do we fall for this paradox in real life? Do we chase the unknown? Not because it's better, but because it might be? So ask yourself, if you're always chasing the envelope you didn't pick, what happens when you finally stop switching? And what if the only real paradox is that you never needed causal loop paradoxes when time breaks itself? It starts with a knock at the door. You open it. There's no one there. But on your doorstep is a box. Inside the box, blueprints for a time machine. No note.
No explanation.
Just instructions. Years later, you finish building it. You go back in time. You place the blueprints in a box and leave them on your own doorstep. The loop is complete. But here's the question. Who invented the time machine? You didn't. The blueprints were already there. They came from nowhere.
No origin. No creator.
Just existence trapped in a loop. This is the core of a causal loop paradox. A sequence of events where a causes B and B causes A, with no clear beginning, no outside source, no first domino, just a perfect circle of cause and effect, endlessly feeding itself. Now imagine something deeper. A woman receives a mysterious book from a stranger. She studies it, obsessively. Years later, she travels through time and hands that same book to her younger self. That book now exists in an eternal loop. No author.
No origin. No explanation.
But it's real. It exists. So where did it come from? In theoretical physics, these aren't just stories. Causal loops appear in real discussions of closed time-like curves, possible paths through spacetime allowed by Einstein's general relativity. Under the right conditions, like inside a rotating black hole or a wormhole, you could, in theory, travel back in time. And if you do, you might become part of a loop you can't escape. Or worse, you might create one. Think of the paradox like this. A future causes the past causes the future, but nothing starts the chain. The information or the object just exists, forever, outside of logic, outside of origin, outside of time, and yet follows every rule. There's no contradiction, no violation of physics. Everything in the loop is self-consistent. It makes sense, except that it shouldn't. Because if nothing creates the thing, how can it exist at all? Now let's go darker. What if your entire life is part of a loop? You're born, you grow, you make choices, and one day you do something crucial that ripples backward and shapes your own beginning. Not by magic, but by time itself. You weren't just the product of your past. You were the architect of it, and you never knew. Some physicists argue this is possible in a deterministic universe, one where everything that happens must happen, and time simply folds in on itself in strange places. But others say no. They say causal loops are a glitch, a paradox, a sign that something about our understanding of time is deeply broken. So ask yourself, if something exists without a cause, without an origin, does it really exist at all? Or is it just an illusion, trapped in the folds of time, echoing itself in the quantum Zeno effect? Can watching freeze time? A man walks into a room. On the table sits a radioactive atom. There's a 50% chance it will decay in 1 hour. If it decays, a detector will fire, and a glass of poison will shatter. The man waits. He glances at his watch. Nothing happens. He checks again. Still nothing. So he does something strange. He watches the atom continuously, every second. He stares and records and measures endlessly. And the atom? It never decays. It's as if time is frozen. This is not fiction. This is the quantum Zeno effect, a real, proven phenomenon in quantum physics, where the very act of constant observation prevents change from happening. Yes, watching something can stop it from evolving. Not metaphorically, literally. In classical physics, this would be absurd. If you throw a ball, it moves no matter how often you watch it. But in quantum mechanics, reality behaves differently. Subatomic particles don't have fixed positions or outcomes. They exist in a cloud of possibilities. They're described by a wave function, a kind of mathematical blur of maybe. And this blur only collapses into one reality, when it's measured, when it's observed. So what happens if you measure it constantly, over and over, rapidly, before it can evolve? You trap it. You pin the particle in place. It's like trying to catch a coin in mid-flip, so often and so fast, that it never lands heads or tails. It never finishes the flip, because every time you look, you reset the game. That's what the quantum Zeno effect does. In the quantum world, observation isn't passive. It's invasive. It alters the system. And if you observe continuously, you can freeze the natural decay of atoms, delay their transitions, and stop quantum systems from changing. You become the warden of time by simply watching. But here's where it gets weird. This effect has been tested. In 1989, physicists at the U.S. National Institute of Standards and Technology used laser pulses to watch beryllium atoms. They showed that rapid observations really did slow down transitions. The atoms stayed in their quantum state longer, simply because they were being watched. Reality hesitated. Time paused, because someone was paying attention. Now imagine what this means. Could it be that reality is reactive? That the universe doesn't fully commit to an outcome until something is there to witness it? And if that's true, what happens if we watch everything? Could we control decay? Could we preserve life? Could we cheat death? Or flip it? What if we're already being watched? What if some cosmic observer, some entity or system, is watching us, keeping the world in place, preventing it from changing too fast, or at all? Are we living in a frozen quantum illusion, a universe where the act of observation itself creates the rules we live by? So ask yourself, if watching something closely enough can stop it from changing, what happens when you find the Monty Hall paradox? The game you always lose. You're standing on a stage. Bright lights, applause, cameras. A smiling game show host points to 3 doors. Behind one of them is a brand new car. Behind the other 2, goats. You get to choose one door. Pick correctly, you win the car. Pick wrong, and you go home with nothing, or worse, a goat. You pick door number 1. The host doesn't open it yet. Instead, he walks over to door #3, opens it, and shows you a goat. Then he turns to you, smiles, and asks, "Would you like to switch to door number 2? Now pause. You've already chosen door number 1. One of the other 2 has been eliminated. So now it's 50-50. Right? Wrong. This is the Monty Hall paradox, named after the real host of a 1960s game show called Let's Make a Deal. And it turns out, switching doors actually doubles your chances of winning. If you stay, your odds are just 1 in 3. If you switch, they jump to 2 in 3. And almost everyone gets this wrong. Even mathematicians have argued over it. Famous scientists, even Nobel laureates, have called it nonsense until they ran the numbers. It defies logic. It goes against instinct. But it's real. Here's why. When you first choose door number 1, the odds of the car being there are 1 in 3. That means there's a 2 in 3 chance the car is behind door number 2 or door number 3. Monty knows where the car is. He will always open a door with a goat. That's the trick. He's not choosing at random. He's narrowing the odds for you by revealing information he already had. So when he shows you a goat behind door #3, the full 2 in 3 chance now transfers to door number 2. Switching isn't just a guess. It's using the game's logic against itself. But here's where it gets deeper. If simply changing your mind can shift the odds so dramatically, if the past choice was worse just because you didn't reevaluate it, what else in life works that way? How many times have we stuck with a bad decision? Not because it was better, but because we made it first? How many times have we refused to switch doors, not out of logic, but out of pride? And think about this. What if reality itself works like Monty Hall? What if the universe isn't just giving us options, but silently revealing goats behind closed doors, pushing us to switch paths, if we're smart enough to notice? So ask yourself, when life shows you a goat, will you stay where you are? Or will you? The absent-minded driver paradox. When knowing hurts you, he's been driving all night. The road is empty. The stars are dim. He's tired, foggy. His mind drifts. He's thinking about a meeting, a memory, a mistake. And that's when the first sign flashes past. Exit A, to nowhere. Not the one he wants. He ignores it. A few minutes later, another sign appears. Exit B, home. That's his stop. But here's the catch. He's absent-minded. And by the time he sees the sign, he can't remember if this is the first exit or the second. Was exit A the one he just passed? Or is this exit A? He hesitates. If this is exit A and he takes it, he'll end up in the middle of nowhere. If this is exit B and he skips it, he'll miss home and keep driving forever. He doesn't know what to do. He has perfect logic, perfect planning, but he's trapped by his own memory. This is the absent-minded driver paradox, a philosophical riddle that shows how, in certain situations, too much logic can fail you. If you can't trust your own awareness, it's like being inside your own mind and suddenly realizing you can't trust the narrator. Let's break it down. Before the drive, the driver makes a plan. If I ever find myself at an exit and I don't know which one it is, I'll calculate the odds and act rationally. So he does the math. There's a 1 in 2 chance he's at either exit A or exit B. He decides that if he reaches an exit and isn't sure which one it is, he'll flip a coin 50-50 and take the risk. But here's where it gets twisted. that very reasoning breaks itself. Because if he knows he'll randomize his decision when he's uncertain, then the only place he'd be making that decision is at exit B. At exit A, he always knows it's the first one. There's no confusion. So the only time he finds himself flipping a coin is when he's at exit B, the one he wants. But the plan he made assumes he might be at either exit. So his logic says, flip a coin. But the situation says, you're at B. So, should he flip the coin or not? It's a paradox, a trap, a perfect loop of logic collapsing on itself, just because the driver forgot where he was. A reminder that even with flawless planning, our actions can fail if we lose context. You can have the right answer and still ask the wrong question. And the real twist? This isn't just a thought experiment. This paradox has been studied in decision theory, economics, and artificial intelligence. It reveals something fundamental about decision-making in uncertain environments. Sometimes knowing too much about your own logic can break it. And that's terrifying, because it means that even if we design a perfectly rational mind, a machine, a future self with no emotions, could still fail. Not because it's wrong, but because it can't remember the past well enough to understand the present. So ask yourself, if you ever find yourself at a crossroads, and you don't know how you got there, can logic still save you? Or will it steer you straight? The free will paradox. Are you choosing, or just obeying? You wake up, you stretch, decide to make coffee, add just the right amount of cream, take that first sip. Feels like you chose all of it. But did you? Now pause for a moment. Was it really you who decided? Or were you just following a chain reaction, set in motion long before you were born? Maybe it wasn't really your decision at all. Maybe it never is. This is the free will paradox. It asks one of the oldest, most haunting questions humans have ever faced. If everything in the universe follows cause and effect, if every thought in your head is triggered by chemicals, neurons, and prior events, then what exactly makes your choices free? Let's go deeper. Imagine you're standing in front of two doors. One leads to the life you're living now, the other completely unknown. And you can choose either. You're told, you have full free will. But behind the scenes, your past, your biology, your habits, your fears, they're all silently pulling the strings. Which door will you pick? The familiar one? The safe one? Did you really choose it? Or were you nudged into it by a lifetime of invisible forces? Now, let's bring in science. Neuroscientists have hooked people up to machines that track brain activity. In some studies, their brains show signs of decision-making seconds before they're consciously aware of deciding. Your brain says yes, before you even realize you've thought about it. So who's really in control? Then comes the determinist view. If the universe is a machine, one domino falling after another, then everything was set in motion at the Big Bang. Every action, every thought, every feeling of love, regret, guilt, joy, all pre-programmed by atoms smashing into atoms. But here's where it twists. If free will doesn't exist, then how can we be held responsible for anything? How can we blame criminals or praise heroes? How can we feel guilt or pride? If our choices aren't ours, what's left? On the other hand, if free will does exist, then what part of us is separate from the brain? What thing beyond neurons and physics is doing the choosing? A soul? A spirit? Some hidden observer? But where is it? Science hasn't found it. And if it is separate, how does it interact with the physical world? How does something immaterial reach into matter and make a body move? This is the paradox. If our actions are caused by physics, we're not free. If they're not caused by anything, then they're random. So are we slaves or dice? And yet, deep down, we feel like we choose. We fall in love. We say no. We regret. We dream. Something in us wants to believe we're steering this ship. But what if we're just watching the waves? So here's the question. When you clicked on this video, when you stayed until the end, was it your choice? Or were you the paradox of the criterion? Can you ever know anything for sure? Imagine you're handed a map. It claims to show the truth. But before you follow it, you ask the obvious question. Who made this map? They say, someone who already knew the truth. So you ask again, but how did they know? And that's when you realize you're stuck in a loop. This is the paradox of the criterion, a mind-bending philosophical riddle that asks one terrifying question. How do you know what you know is really true? And what if the very tools you use to decide what's true are the very things that might be wrong? Let's step into the mind of the ancient philosopher Sextus Empiricus. He asked two simple questions. What do we know? How do we decide what's true? What standard or criterion do we use? Seems reasonable, right? But here's where the problem starts. To answer question 1, what do we know? We need a criterion, a tool to measure truth. But to trust any criterion, we first need to know that it's valid. And suddenly we're caught, because we can't answer what we know without a trusted tool. And we can't trust the tool unless we already know what truth looks like. It's like trying to test your ruler by measuring it with itself. It'll always seem right, even if it's wildly off. Or like trying to verify if your brain is working by using your brain. What if your thinking is broken? How would you ever know? This is where skepticism creeps in. Some philosophers say, well, we just have to start somewhere. Trust one thing, build from there. But others say, isn't that blind faith dressed up as logic? Because if your foundation might be cracked, how strong can the house really be? And yet, we live our lives believing things. That the sun will rise tomorrow. That our memories are mostly true. That science or logic or experience can tell us what's real. But have we ever proven that our tools of knowing are reliable? Or are we all just guessing with confidence? There are 3 traditional responses to this paradox. Skepticism, we can't know anything for sure. Maybe knowledge is impossible. Dogmatism, we assume a starting point, like reason or sense perception, and build from it. Methodism, we try to define the right method first, and trust that it will lead us to truth. But here's the twist. Every path loops back into itself. To choose a method, you need a criterion. To trust a criterion, you need to know it works. To know it works, you need a method. Round and round it goes. It's not just abstract philosophy either. This paradox touches everything. Science, how do we know the scientific method leads to truth? Religion, how do we decide which spiritual experiences are valid? AI and knowledge systems, how do we program a machine to know anything without circular logic? So what are we left with? Are we lost in an ocean of doubt? Maybe. Or maybe the real message is this. True wisdom doesn't start with answers. It begins with the courage to ask if our answers make sense at all. So before you trust your next belief, your next judgment, your next certainty, ask yourself, what tool are you using to measure the truth? And who gave you the barber paradox? A question so simple it destroys logic. In a quiet village, nestled somewhere beyond time and maps, there lives a barber. And this barber follows a strict rule. He shaves all the men in the village who do not shave themselves. Sounds simple, right? But then someone asks a question. Who shaves the barber? And suddenly reality breaks. If the barber doesn't shave himself, then by the rule he must shave himself. But if he does shave himself, then by the rule he must not shave himself. He can't do it, but he also must. And with that single question, logic collapses. This is the barber paradox, created by British philosopher and mathematician Bertrand Russell in 1901. And it's not just a fun brain teaser. It exposed a critical flaw in the very foundations of mathematics and logic. A contradiction hiding in plain sight. Back then, mathematics was believed to be built on unshakable rules. People thought you could define everything in the universe using sets. Collections of things. A set of cats. A set of stars. A set of ideas. Then Russell asked a strange question. What if we create a set of all sets that do not contain themselves? Like, a list of all lists that don't list themselves. Let's call it set R. Now ask, Does set or contain itself? If it does, then by definition it shouldn't. If it doesn't, then by definition it should. Just like the barber can't, but it must, but it can't. This wasn't just a headache. It was a disaster. It meant the very logic we used to build mathematics could lead to contradiction. A logical black hole. And if one paradox could sneak in, how many others were waiting? The ripple effects were enormous. Mathematicians scrambled to fix their foundations. Russell himself tried to build a new logical system to avoid the paradox, but it was brutally complex. Later, others like Kurt Gödel showed that any system powerful enough to express basic math will always contain truths it cannot prove. In other words, some questions can be asked inside the system, but can never be answered within it. And that shook the very meaning of truth. So the barber paradox isn't really about barbers. It's about the limits of thought itself. About how even in perfect logic, a simple question can tear a hole in reality. We like to believe the world runs on rules, that everything fits somewhere, that if you define things clearly enough, you'll avoid contradiction. But the barber reminds us, sometimes the contradiction is the definition. So next time you think you've explained it all, ask yourself, who shaves the barber? And if the answer doesn't exist, what else? Newcomb's paradox. What if the future already knows your choice? You walk into a room. In front of you sit two boxes. One is transparent. You can see it holds $1,000. The other is opaque, sealed tight. You're told it either contains $1 million or nothing. But here's the twist. A powerful predictor, an entity with a near-perfect record of guessing human behavior, has already made a decision. If it predicted you would take only the opaque box, it placed $1 million inside. If it predicted you would take both boxes, it left the opaque one empty. And now it's your move. Do you take both boxes? Or just one? Welcome to Newcomb's paradox, one of the most maddening and unsettling thought experiments in modern philosophy. A scenario where free will, prediction, and self-trust collide like particles in a quantum storm. Let's break it down. Logically, the argument goes like this. If the opaque box has already been filled or emptied, then your choice can't change it, right? So why not take both boxes? Worst case, you get $1,000. Best case, you get $1,001,000. It seems like the obvious, rational move. But here's where the paradox kicks in. People who take only the opaque box tend to win the million, because the predictor knew they'd do it. And it was right. Again. So, should you ignore logic and trust the prediction? Can someone or something really predict your choice before you even make it? If so, do you actually have free will? This isn't just a philosophical trick. The predictor is assumed to be nearly infallible. It has correctly predicted thousands of people before you. And you know this. So now your brain splits. One part says, be logical. Take both boxes. The other whispers, the predictor already knows. It's too late to outsmart it. It feels like a psychological trap. But what if it's not a trap, but a mirror? This paradox has tormented philosophers, economists, and scientists for decades. Because it forces us to confront something terrifying. What if the universe isn't waiting for you to decide? What if it's already decided what you will do? Some say Newcomb's paradox shows that free will is an illusion. Others argue it's about causality, how the future might be shaped by predictions made in the past. Some invoke quantum mechanics, suggesting the act of choosing collapses possibilities into one fixed outcome. Still others say it's a failure of logic itself, proof that rational thinking can't always beat a cleverly designed game. But all of them are haunted by one question. If someone could predict your every move, could you ever surprise them? Even stranger, in real life we already act like predictors control us. Think about algorithms, your recommended videos, your social feeds, your search results. They seem to know you, sometimes better than you know yourself. So what if Newcomb's paradox isn't a game? What if it's just the world we already live in? So, now it's your turn. Two boxes sit before you. One choice will define you. The The predictor already knows what you'll do. The crocodile paradox, the reptile that broke logic. Imagine this. You're standing on the edge of a river. A crocodile has just snatched your child from the water. But instead of vanishing into the depths, it speaks. Yes, it talks. And it makes you an offer. If you correctly predict what I will do next, I'll give your child back. But if you're wrong, I keep them. Your mind races. You look the creature in its ancient, emotionless eyes. And you say, "You're going to return my child." Then, silence. The crocodile stares. And suddenly, the rules of reality start to fold. Because now, no matter what the crocodile does, creates a contradiction. Welcome to the crocodile paradox, a mind game that seems so simple, yet breaks the very foundations of logic and truth. Let's slow it down. There are two possibilities. The crocodile gives the child back. In that case, your prediction was correct, so it should return the child. All good. The logic checks out. The crocodile doesn't return the child. Now here's the twist. If your prediction was that the child would be returned, and the crocodile doesn't return them, then your prediction was wrong. But if your prediction was wrong, then the crocodile is allowed to keep the child. But wait, that means your prediction was right, because it wasn't returned. But if it was right, then it should return the child. But then your prediction becomes wrong again. And around it goes. An endless loop of logic short-circuiting itself. It seems silly at first. A talking crocodile? A riddle? But hidden in this ancient brain teaser is something much deeper. It forces us to ask, can logic always decide what's true? Or are there situations where truth itself becomes undefined? The crocodile paradox is part of a family of self-referential paradoxes. Like the liar paradox, this sentence is false. It's also related to Russell's paradox, which shattered the foundations of set theory. And like all great paradoxes, it reveals a disturbing truth. Sometimes the rules we rely on to make sense of the world collapse under their own weight. Some philosophers say the paradox exposes flaws in how we define knowledge and truth. If knowing something depends on it happening, but the thing only happens if you know it, what does knowing even mean? Others say this is the limit of language itself. That when we tie logic into a knot, what breaks isn't reality, but our description of it. So next time you think logic is perfect, remember the crocodile, a creature that didn't need teeth to bite through reason. It only needed a question. And now you've heard the paradox. So tell me, what do you predict the crocodile will do? And if you're right, does that mean the whole paradox? A tear in space and time. Imagine this. You're standing in the vacuum of deep space. Nothing but darkness and silence surrounds you. Ahead of you drifts a small, massive object. A black hole. But not just any black hole. Perfect one. Calm. Silent. Mathematical. And then something strange happens. You measure the gravitational field around it. You record everything, the shape, the strength, the way light bends around it. And now, with that data, you try to figure out what's inside. But you can't. Not because you're missing data, but because the universe refuses to answer. This is the heart of one of the strangest paradoxes in modern physics. The whole paradox. It was born from the mind of physicist John Earman, and it challenges one of the most sacred ideas in Einstein's theory of general relativity. That the shape of spacetime and everything in it can be predicted if you know the rules and the starting conditions. Seems fair, right? If you knew every particle, every force, every law, you should be able to tell what the universe will do next. But the whole paradox says, no, not always. Here's the setup. In general relativity, you can describe a patch of spacetime using mathematical fields, things like gravity, curvature, mass, and energy. Now imagine you define all those fields outside of a small, empty region, what physicists call the whole. You're not touching the whole itself. You're only describing everything around it. Then you use Einstein's equations to solve for what must be inside. But shockingly, the equations don't give just one answer. They give infinitely many. That's right. Same outside world. Same laws, same setup, but the inside could be anything. The math says, sure, that could be it. Then, wait, this other version works too. Reality, it seems, is no longer deterministic. And suddenly, the idea that the laws of physics control the future begins to unravel. Einstein hated this. His entire vision of the universe was based on the idea that spacetime is a smooth, continuous fabric. That if you know the shape of the fabric here and now, you can predict its shape tomorrow. But the whole paradox says spacetime is like a puzzle, with missing pieces that can be filled in any number of ways. And the universe doesn't care which one you pick. So, what does this mean? Are Einstein's equations broken? Are they too powerful? Do they allow too many realities to emerge from the same setup? Some physicists tried to fix the problem by adding extra rules, defining the system in ways that force one solution and not many. But that's just sweeping the mystery under the rug. Because if the universe really does work like this, then reality might not be a perfect, predictable machine. It might be something else, a story with missing pages, where the ending can be rewritten, even if the beginning stays the same. This isn't just about a hole in spacetime. It's about a hole in how we understand reality. And the terrifying possibility that determinism, the idea that every effect has a cause, might not be fundamental at all. That even with all the knowledge in the cosmos, some things remain unknowable. So here's the question. If the universe doesn't need a reason to choose one reality over another, then what is driving the future? And worse, what if the black hole that knows too much? Let's begin with a crime scene. But not just any crime scene. This one is cosmic. A star has died. It collapsed under its own weight and vanished into a black hole. Everything it once was, its atoms, its heat, its identity, was swallowed by darkness. And in that instant, something strange happened. Information disappeared. Or did it? This is one of the deepest mysteries in the universe. A puzzle that's haunted physicists for decades. It's called the black hole information paradox. And it might rewrite everything we know about reality. First, a quick question. What happens when you burn a book? Its pages turn to ash. The ink fades. The words vanish. But not completely. In principle, if you had perfect knowledge of all the molecules, you could reconstruct the book. Its information, the words, the story, the message, still exists. This is what physics tells us. Information can't be destroyed. Not even in the heart of a star. But now imagine throwing that book into a black hole. The pages are gone. The molecules, crushed. The light, trapped forever. Now ask, where did the story go? This is where the paradox begins. According to general relativity, black holes are simple. They have no hair, no details. All you need to describe one is three things: mass, charge, and spin. Nothing else matters. It doesn't care if it swallowed a book or a boulder, a person or a planet. Everything becomes the same. It's as if reality gets wiped clean. No records, no memory. But that's a problem. Because quantum mechanics, the other great pillar of physics, says information is eternal. The universe remembers. Even if it's scrambled, hidden, distorted, the data can't just vanish. But when a black hole evaporates through Hawking radiation, as Stephen Hawking famously proposed, all that comes out is random thermal noise.
No signature.
No echo of what went in. No way to reverse it. That's the paradox. If black holes destroy information, then quantum theory is wrong. If quantum theory is right, then black holes must store information somehow. But where? Some say the information hides at the event horizon, like a hologram painted on the surface of the black hole. This is the holographic principle, a radical idea suggesting that everything we know may just be a projection. Others argue that the information comes out with the Hawking radiation, but in such a subtle way we haven't figured out how yet. Some even believe that black holes don't really destroy anything. They just teleport the information to another universe. And then there's the idea that we've misunderstood black holes completely. That they don't evaporate in the way we thought. or that time itself behaves differently near the end. Physicists have been fighting over this for decades. Stephen Hawking once bet that information was lost forever. Years later, he reversed his stance. He admitted defeat, but never found a complete answer. Even today, some of the brightest minds, like Leonard Susskind, Juan Meldacena, and Gerard T. Hooft, are still searching for the truth. So why does it matter? Because information isn't just about data. It's about reality. If it can truly disappear, then cause and effect may break down. The past may no longer determine the future, and the universe itself may be capable of forgetting. Think about that. Your thoughts, your memories, everything that makes you you, could be erased. Not just physically, but fundamentally. No trace, no shadow, just gone. So here's the question. If a black hole can delete the universe's memory, what happens when you fall in? Does the story of your existence live on somewhere, somehow? Or is there a place in this universe where reality itself can... The paradox that destroys logic itself. Let's play a little mind game. Imagine a sentence written in bold letters on a white wall. It says, "This sentence is false." Now, is it true? If it's true, then what it says must be correct. So the sentence is false. But if it's false, then what it says is not correct. Which means the sentence is actually true. It loops, twists, it eats itself. And suddenly, logic breaks. This is the self-reference paradox. One of the strangest, most dangerous puzzles in the history of human thought. It may seem like a joke, a trick of words, but don't be fooled. This paradox has shaken the very foundations of mathematics, logic, philosophy, even computer science. It first appeared in ancient Greece. The philosopher Epimenides said, "All Cretans are liars," while being a Cretan himself. It was cute, clever, but over time this idea evolved into something far more serious, something terrifying. In the 20th century, mathematicians tried to build a perfect logical system, a framework where every truth could be proven and every contradiction eliminated. And then came a man named Kurt Gödel. He crafted a sentence within this system that said, essentially, this statement cannot be proven, just like our earlier loop. If the statement can be proven, then the system has proven something false. But if it cannot be proven, then it must be true, and the system can't prove it. Either way, the system fails. With that one idea, Gödel didn't just play with logic. He broke it. He showed that every complete system of logic is also incomplete. There will always be truths it can't prove. This was the beginning of a revolution. Self-reference, it turns out, is a virus in logic. A paradox that acts like a glitch in the matrix, pops up in programming when a piece of code refers to itself endlessly. It appears in biology, when the brain tries to understand the brain. It even shows up in artificial intelligence, when a system tries to predict its own future behavior and fails. Each time it creates a loop, contradiction, a wall we can't cross. It's like trying to see your own eyeball without a mirror. Now think bigger. What happens when the universe becomes self-aware? When we, small, conscious creatures, look out into the cosmos and try to explain everything, including ourselves. Are we just building bigger and bigger loops? Are we trapped in a paradox of self-reference, doomed to never find the final answer because we're part of the question? In physics, some believe this is why we struggle with consciousness, why we can't define what it means to know or to be aware, because the thing trying to know is also the thing being known. The mirror is staring into itself, and the deeper you go, the more it cracks. So here we are, caught in a strange loop, asking questions about truth, logic, and meaning, using the very tools that might be fundamentally limited by paradox. Tools that can describe galaxies and black holes, but might fall apart when turned inward. So here's the question. If we are the system trying to understand itself, is there a truth that exists beyond what we can ever prove? Or are we all just lines in a sentence that says, this story, when saving money destroys the economy? Let me ask you something strange. What if being wise with your money could crash the entire economy? What if millions of people doing the right thing, saving for the future, somehow led to recession, unemployment, and national collapse? It sounds impossible, but it's real, and it's called the paradox of thrift. Picture this. You're nervous about the future. Prices are rising, your job feels unstable, and there's talk of a downturn. So you make the responsible choice. You stop spending. No more restaurants. No new clothes. You cancel your vacation. You save more. You hold tight. And you feel a little safer. But here's the twist. So does everyone else. Now businesses feel the pain. Fewer customers. Less demand. Restaurants close. Shops go bankrupt. Your neighbor loses her job. So does your cousin. And then maybe you do too. Because when everyone saves at the same time, no one's spending. And when no one's spending, there's no income. That's the paradox. The very act of saving, meant to protect you, ends up hurting everyone, including you. The idea was popularized by economist John Maynard Keynes. During the Great Depression, he argued that while thrift is good for an individual, it can be devastating for a society in crisis. Why? Because one person's spending is another person's income. Money has to move for the system to live. When it stops, the engine stalls. It's the opposite of what we're taught. We grow up hearing that saving is always smart. Don't waste money. Be frugal. Prepare for hard times. And that's still true on a personal level. But in moments of economic panic, when everyone does it together, it becomes destructive, turns a slowdown into a crash. Governments try to fight this with stimulus packages, interest rate cuts, and spending programs. They pour money into the system to keep it flowing. Because if they don't, the spiral deepens. Savings rise, spending drops, businesses close, jobs vanish, fear grows, and the loop repeats. It's like trying to keep a heart beating when every cell in the body refuses to pump. So now we're left with a strange question. Can doing the right thing be wrong if everyone else does it too? And if so, who decides when to save and when to spend? So here's the real paradox. If saving money can destroy an economy, could spending recklessly actually be what saves it? Or are we trapped in a system where logic for the individual, the edge of the universe, shouldn't exist? The causal horizon paradox. Let's begin with a simple question. Why is the universe so smooth? Why does it look the same in every direction? Same temperature, same density, same glow from the Big Bang? Now here's the problem. Those regions, billions of light years apart, were never in contact with each other. They've never shared a message, not even a photon. They are too far apart to have causally influenced each other. And yet, they look identical. How? This is the causal horizon paradox. A cosmic riddle that challenges everything we think we know about time, light, and the birth of our universe. The universe has a speed limit, the speed of light. Nothing, not a thought, not a signal, can travel faster. So at the moment of the Big Bang, the universe should have started expanding from a single point, and only regions close enough to each other could have exchanged heat, energy, or information. But that's not what we see. When we look at the cosmic microwave background, the afterglow of the Big Bang, we find something shocking. The entire sky glows at almost exactly the same temperature, to a precision of 1 part in 100,000. It's like billions of ovens across the cosmos were all set to the exact same setting, even though they never spoke. That shouldn't be possible. It's like walking into a room with two strangers from opposite ends of the earth, wearing the same clothes, humming the same tune, with the same memories, and they swear they've never met. So, what happened? How did parts of the universe beyond each other's causal horizon, beyond any ability to exchange information, end up in perfect sync? One idea is called cosmic inflation. It suggests that, just after the Big Bang, the universe expanded faster than light. Not violating physics because it wasn't matter moving, it was space itself stretching. This means everything was once close enough to share heat and energy. and then, in a flash, was torn apart faster than any signal could travel. Inflation would explain the uniformity. But here's the twist. We don't know why inflation started, or stopped, or what caused it. We don't even know what inflated. It solves one paradox, by opening the door to even deeper mysteries. And there's another theory, a weirder one. What if time didn't work the way we think? What if space and time were somehow connected in a way we can't fully grasp yet? Some physicists think the causal horizon might be an illusion, that what we see as distance or disconnection could be unified on a deeper level of reality, a level we haven't discovered. The paradox remains. Why does a universe that shouldn't be connected act like one unified whole? How did the sky synchronize itself without ever exchanging a message? So here's the question that haunts cosmology. If distant parts of the universe were never supposed to meet, then what stitched them together? And what if they were never separate to begin? The exam that broke logic. The unexpected exam paradox. Imagine this. A teacher walks into class and makes an announcement. There will be a surprise exam next week, she says. It will happen on one day, Monday through Friday, but you won't know which day. Until that morning. The students nod, nervous but curious. A surprise exam. Sounds simple, right? But then one student thinks, and starts to reason, and that's when the whole thing breaks apart. Wait, he says to his friends. It can't be on Friday, because if we make it to Thursday night with no exam, we'll know it has to be Friday. And that wouldn't be a surprise. They agree, so Friday is out. But now, he says, it can't be Thursday either, because if Friday's ruled out, and the test hasn't come by Wednesday night, then it must be Thursday. Again, no surprise, so Thursday is out too. Then Wednesday, then Tuesday. Eventually, they convince themselves the surprise exam is logically impossible. But here's the twist. On Wednesday morning, the teacher walks in and hands out the test. And the class, totally shocked. She smiles and says, "Told you it would be a surprise." This is the unexpected exam paradox. Also called the paradox of the surprise test. It's a brain-bending scenario where logic turns against itself. Because the students used perfect reasoning to conclude the test couldn't happen. But when it does, they are still surprised. So what went wrong? Some say the paradox lies in language, that the phrase surprise exam is just too vague, too slippery. Others think it exposes a flaw in self-referential logic. When your prediction includes your own future thoughts, it collapses. And some go further. They say it reveals something deeper about human knowledge, that we can't perfectly predict our own beliefs, that sometimes the very act of expecting a surprise destroys it. It's like trying to sneak up on yourself. But the paradox has real consequences. It's used in philosophy to question what we mean by knowledge. It's used in computer science to explore recursive reasoning. And in epistemology, how we know what we know. It's a ticking bomb in the middle of logic itself. Because if you can logically prove that something can't happen, and then it does, what does that say about logic? So here's the question. If reasoning can be flawless, and still lead to false conclusions, can we ever truly trust what we know? Or are some surprises beyond reason? The word that shouldn't describe itself. The Grelling-Nelson paradox. Let's play a word game. Some words describe themselves. Others don't. The word short is a short word, so it describes itself. It's autological. But the word long isn't long. It doesn't describe itself. It's heterological. Now here's the trap. A beautiful, silent trap hiding inside language itself. What about the word heterological? Does it describe itself? Let's think it through. If heterological is heterological, then it doesn't describe itself. But wait, it just did. That's a contradiction. So maybe it isn't heterological, maybe it's autological. But if it's autological, then it does describe itself, which means it should be heterological. Another contradiction. We're stuck. Language has collapsed in on itself. This is the Grelling-Nelson paradox, a riddle made entirely of words, with no story, no numbers, no equations, just meaning eating its own tail. And yet it's powerful enough to shake the foundation of logic. It was first proposed in 1908 by philosophers Kurt Grelling and Leonard Nelson. At first glance, it seems harmless, a clever linguistic puzzle. But it's not. It's a self-referential monster, a paradox born from the very tools we use to describe reality. It's a cousin of Russell's paradox, which broke set theory. It's related to the liar paradox. This sentence is false, but this one doesn't need sentences or sets. It uses the meanings of words themselves, forces us to ask, can we build a consistent system of logic that includes words describing words, without collapsing into contradiction? Some thinkers believe this paradox reveals the limits of language. Others say it shows why any system that refers to itself, whether language, logic, or consciousness, will always carry the seeds of its own failure. And in the age of artificial intelligence, these paradoxes aren't just philosophical toys. They're warnings. Because machines that use language might also fall into these traps. So how do we fix it? Some propose stricter definitions or layered languages where a word can't describe itself from within the same system. Others say maybe we can't fix it. Maybe there are limits to what we can say and what we can know. So here's the question. If a single word can undo logic, how stable is the reality we've built on language? And what else might collapse if we describe it too precisely? The sentence that ate itself. The Quine paradox. Let's begin with something simple. This sentence has 5 words. It's true. Nothing strange. This sentence is false. Now it's tricky. A classic paradox. But now, imagine a sentence so bizarre, so self-consuming, that it doesn't just contradict itself, quotes itself. Here it is. Yields falsehood when preceded by its quotation, yields falsehood when preceded by its quotation. Read it again. The sentence literally refers to itself, not by saying, this sentence, but by repeating its own structure. It eats its own tail like a verbal Ouroboros. And what it says is that if you quote it and then follow it with the sentence itself, you get a falsehood. But wait, that's exactly what the sentence is. It is its own quotation followed by itself. So if it yields falsehood when preceded by its quotation, and it is preceded by its quotation, then the sentence is false. But it's saying it's false. So it's true or false again. We spiral. This is the Quine paradox, named after American philosopher Willard Van Orman Quine, who didn't just want to confuse you, he wanted to test the boundaries of meaning itself. This paradox is a linguistic time bomb, because it uses no pronouns, no sneaky phrases like, this sentence. It builds a perfect, airtight loop, a sentence that refers to itself structurally. And that's what makes it so dangerous. Why does this matter? Because language isn't just how we talk. It's how we think. It's how we build computers, how we write code, how we create rules for truth and logic. But the Quine paradox reveals a deep truth. Even with perfect structure, logic can fold in on itself. Truth can slip away. Quine's sentences challenge how we define meaning. They don't just play with language. They bend reality by showing how even the cleanest logic can get caught in an endless mirror hall. They haunt programming languages, mathematical logic, even artificial intelligence. Because once a machine starts to understand sentences like this, sentences that reference themselves without saying so, what does that mean for truth? What does it mean for consciousness? Some say the only way out is to build levels of language, like floors in a building where each level can talk about the one below it, but not about itself. Others say that's just delaying the paradox, postponing the moment when the system eats itself. And still others ask, maybe self-reference isn't a flaw, but the birthplace of awareness? So here's the question. If a sentence can know itself, what happens when a machine does? And when logic turns inward, does it find truth? Or something else, the infinite gamble that breaks your brain. The St. Petersburg paradox. Imagine someone walks up to you and says, "I'll flip a coin. If it lands heads on the first flip, I'll give you $2. If it lands heads again for dollars, then $8, then $16, then $32. Every time it lands on heads, the prize doubles. They'll keep flipping until it lands on tails. Then you get nothing beyond that last amount." Sounds fun, right? Now here's the twist. You have to pay to play. How much would you pay for this game? Take a second. Think about it. Most people say something like $10, maybe $20. But here's the trap. Mathematically, this game is worth infinity. Not figuratively, literally. Let's break it down. There's a half chance of winning $2, 1/4 chance of winning $4, 1/8 chance of winning $8. So the expected value is and 1/4 times $4 equals $1. 1/8 times $8 equals $1. And so on. Each term equals $1. Forever. Add it up and you get infinite dollars. So rationally you should pay any price to play. But no one does. And no one ever would. This is the St. Petersburg paradox. A centuries-old puzzle that tears apart our ideas of logic, risk, and value. It was introduced in 1713 by Nicholas Bernoulli, and it hasn't stopped haunting mathematicians since. Because it reveals a strange truth. What makes sense on paper doesn't always make sense in the real world. Why don't people pay thousands or millions to play? Because something deep in our brains says, this isn't right. We're not wired for infinity. We care about risk. We care about utility. We care about reality. Sure, the coin could land heads 100 times, but the chance of that is astronomically low. And our real-world wallets? They're not infinite. Economists tried to fix the paradox. Daniel Bernoulli, yes, same family, proposed something called diminishing marginal utility. The idea that $100 means more to a poor person than to a billionaire. That helps a bit, but not completely. Even with diminishing returns, there's still a version of the paradox hiding in the shadows. Modern versions use computer simulations, behavioral economics, bounded utility. Some even invoke cognitive biases. But none of them truly solve it. Because at its core, the St. Petersburg paradox isn't just about money. It's about how we think, how we value chance, how we fear loss, how we make decisions under the illusion of logic. It's about the cracks in our supposedly rational minds. So next time someone offers you the ultimate gamble, remember math might say infinite, but your instincts might say, no deal. And maybe they're right. So here's the question. If our brains can't handle infinity, does that mean the universe is rigged to confuse us? And what if infinity is the paradox hidden in a dictionary? The Berry paradox. What if I told you a simple sentence could cause logic itself to collapse? No time travel, no quantum physics, just words. Ordinary, everyday language, used in a certain way, that quietly creates a loop so destructive. It puzzled the greatest minds in mathematics. This is the Berry paradox. And it all begins with this sentence. The smallest positive integer not definable in under 11 words. Seems harmless, right? Just a weird way of picking a number. But think about what it's saying. We're talking about numbers that can't be described in under 11 words. So, we're trying to point to a number that has no short description. But wait, the smallest positive integer not definable in under 11 words. That's a 10-word description. So we just defined the number using fewer than 11 words. And now it's no longer undefinable, which means it doesn't fit the description anymore. So the sentence cancels itself out. But if it doesn't define that number, then the number still exists, which means the sentence should work. And we loop, over and over. Sounds absurd. But this tiny tangle of logic, first noticed by British philosopher G.G. Berry and later explored by logician Bertrand Russell, punches straight through the heart of language, mathematics, and even computer science, because it exposes something terrifying. Even our cleanest, clearest tools, words, can betray us. See, we often assume that language is safe, that definitions are stable, that words can build solid walls of logic. But the Berry paradox proves that when you define something in terms of what it isn't, you open the door to contradiction. And that door doesn't close easily. This paradox connects to Russell's paradox, to Gödel's incompleteness theorems, even to the limits of artificial intelligence. Because once language begins referring to itself, once we define things by their own undefinability, we enter a strange, recursive world. A world where meaning unravels, where definitions eat themselves, where a simple sentence destroys certainty. So what is the solution? Some say the answer lies in formal languages, strict symbolic systems where vagueness can't survive. Others say the paradox isn't a bug, it's a warning that human language, with all its beauty and complexity, was never built to be airtight. And yet, the Berry paradox persists because it doesn't rely on fantasy. It doesn't require black holes, time machines, or multiverses, just a dictionary and 10 ordinary words. So here's the question. If we can create a paradox just by describing something, what happens when we try to describe reality itself? Can language truly capture truth? Or is everything we say just a riddle in why your friends have more friends than you? The friendship paradox. Have you ever felt like everyone around you has a better social life? Like your friends are more popular, more connected, always invited to things you weren't even aware of? Here's the unsettling truth. You're not imagining it. Statistically, it's true. And it's not just in your head. It's a real mathematical phenomenon. It's called the friendship paradox. And once you understand it, you'll never look at your relationships the same way again. The paradox was first noticed by sociologist Scott Feld in 1991. He found something strange while studying social networks. On average, your friends have more friends than you do. That's not a self-esteem issue. It's mathematically inevitable. Here's how it works. Imagine a small social network. One person has 100 friends. Another has 10. Another has just 2. If you randomly pick someone and ask, "Hey, how many friends do your friends have?" you're more likely to end up in the circle of the popular person. Why? Because the popular person is connected to more people. They show up in more friend circles, more chances to be picked. So your sample of friends is skewed. You're not seeing the average person. You're seeing the most connected ones over and over again. And that makes you feel like the odd one out, even if you're not. The friendship paradox appears everywhere. In classrooms, on social media, even in cities. People think their classmates are doing better, that everyone else has more followers, that their neighbors are more social, because they're comparing themselves to a distorted reality, a mirror that always reflects someone with more connections. It's not envy, it's math. But this paradox goes deeper. It doesn't just twist how we see ourselves. It affects how diseases spread, how ideas go viral, how influence flows through society. Epidemiologists use it to predict who's more likely to catch a virus early. Marketers use it to target influential nodes in a network. And platforms use it to recommend content you didn't ask for, because they know your friends are statistically more connected than you. The paradox powers the system, and most of us never notice. So what does it mean for you? Maybe the next time you scroll through someone's perfect photos, or see your friends out without you, or wonder why you feel left behind, remember, the network is biased. Your view is distorted. You're not a loner. You're just standing in the wrong spot of the graph. But here's the real mystery. If our friends have more friends than us, and their friends have more friends than them, where does it end? Who is the true center of the social universe? And are they the paradox hiding in every book? The preface paradox. Imagine holding a book written by a brilliant author. A book filled with facts, arguments, and careful reasoning. Every chapter was revised, double-checked, and backed by evidence. The author believes in everything they wrote. But then you flip to the front of the book, the preface, and there it is. One quiet sentence that changes everything. Despite my best efforts, I may have made some errors in this book. Wait, what? The author just said they believe every claim inside the book is true. So why admit there might be mistakes? Welcome to the preface paradox. A paradox that hides in plain sight in almost every piece of serious writing ever published. And it quietly exposes something uncomfortable about how humans believe things, especially when we think we're being rational. Let's break it down. Imagine a historian writes a book with 50 factual claims. Each claim is well-researched. Each one is supported by sources. So the historian reasonably believes each one is true. But based on past experience, they also know, I've written books before, and even with editing and fact-checking, there's usually one or two mistakes. So, logically, they also believe at least one of these 50 claims is probably false. But here's the twist. If you believe each individual claim is true, how can you also believe at least one is false? That's the paradox. You believe in every part, but not in the whole. This isn't just a clever riddle. It exposes something deeper, something we all wrestle with whether we realize it or not. It's about rational uncertainty. You can be confident in every belief you hold, and still step back and say, some of these beliefs might be wrong. And that's not contradiction. That's honesty. But logic doesn't like it. Because in formal reasoning, if you accept all the parts, you're supposed to accept the whole. And if you reject the whole, you must reject at least one part. But the preface says otherwise. This paradox challenges more than just authors. It confronts scientists, philosophers, and even people of faith. Because no matter how much evidence we gather, no matter how confident we feel, there's always that whisper of doubt. I might still be wrong. And if we're too certain, we become rigid, dogmatic. If we're too doubtful, we become paralyzed, unable to trust anything. So how do we live between those two extremes? How do we believe and still stay humble? Some say the answer lies in probability. We believe things to a degree, not absolutely. Others argue that knowledge must always include room for error, because truth isn't a checklist, it's a journey. And some just live with the paradox, because maybe uncertainty isn't a flaw. Maybe it's the price of being a thoughtful human in a messy world. So here's the question. If we can't fully trust even our most careful beliefs, then what does it really mean to know anything at all? And if every preface ends in doubt, what about the story why seeing a green apple proves ravens are black? The raven paradox. A black raven sits silently on a tree branch. His feathers shimmer like spilled ink. His eyes still ancient knowing. You look at it and think, all ravens are black. Feels obvious, unshakable, truthful. But here's the strange part. According to logic, if you believe that all ravens are black, then a green apple, yes, a green apple, actually helps prove you're right. Wait, what? Welcome to the raven paradox. A quiet thought experiment that twists the way we understand logic, evidence, and even truth itself. It starts with a simple rule. All ravens are black. That's a universal statement, which means anything that's not black should also not be a raven. So if you see a red bird, fine, not a raven.
No contradiction.
If you see a black raven, good, supports your belief. But now it gets weird. What happens when you see a green apple? It's not black, it's not a raven. And according to pure logic, that also supports the idea that all ravens are black, because it's a thing that follows the rule. If it's not black, then it's not a raven. So congratulations, that apple in your fruit bowl just added weight to a theory about birds you've never met. This idea comes from the logician Carl Hempel in the 1940s. He asked a disturbing question. If all ravens are black is logically equivalent to all non-black things are non-ravens, then shouldn't any non-black, non-raven count as evidence? A white shoe, a yellow pencil, a green apple, they all seem to confirm the rule, even though they feel totally unrelated. But deep down, something feels off. How can staring at office supplies or bananas possibly strengthen a theory about birds? Is logic broken? Or is our understanding of logic broken? That's the heart of the paradox. It forces us to ask, what counts as real evidence? Is it just what fits the rule? Or should it be directly relevant? Because if we accept that everything in the world either confirms or denies every rule we make, then the universe becomes absurdly noisy. Some philosophers argue that the paradox only works in a vacuum, a world where we know almost nothing, where every tiny clue matters. But in the real world, we already know that green apples aren't ravens. So they tell us nothing new. Others say it highlights a deeper flaw, that logic alone can't capture the way humans actually reason. Because we don't just count facts, we weigh them. We care about relevance, context, intuition, and maybe that's the point. The Raven paradox isn't about birds or apples. It's about how fragile logic becomes when you try to stretch it into reality. It reminds us that even airtight reasoning can lead to outcomes that feel completely wrong. And yet, those outcomes might still be valid. So the next time you see a green apple, ask yourself, is this a meaningless piece of fruit? Or a quiet whisper from the universe, telling you something about the color of ravens? And if that's true, what else are we proving? The strange truth about elevators. The elevator paradox. You step into your apartment building. It's 10 floors high. You press the elevator button and you wait, and wait, and wait. Eventually, the doors open. But once again, it's full of people coming down from the higher floors. And if you've ever lived in a tall building, you might have felt it too. Why do I always run into elevators going down instead of up? It feels like the universe is playing a trick on you. But it's not bad luck. It's not your imagination. It's a paradox. And it reveals something deeply unintuitive about how we experience reality. Let's break it down. In a normal building, you'd think elevators go up and down equally. 50% up, 50% down. So, if you enter the elevator randomly, you'd expect to meet just as many people going up as coming down. Right? Wrong. In real life, you meet far more people going down. And it's not because of human behavior. It's a quirk of probability, hidden in plain sight. Here's the twist. Most people live on higher floors. So when they leave home, they take the elevator down. Which means the elevator stops on more high floors to pick up people going down than it does to pick up people going up. And since the elevator spends more time coming down, it's more likely that when you call it, it's already going down. It's like fishing in a stream where the current flows only one way. You keep catching the same direction, not because it's more frequent, but because it feels more frequent. This is called the elevator paradox. It's a cousin of something known as sampling bias. You see, you're not observing the elevator's entire journey. You're only seeing the moments when you interact with it. And those moments aren't random. They're shaped by patterns you don't even notice. The paradox isn't in the elevator's behavior. It's in your perspective. Think of it like this. Imagine there are 100 people in the building. 80 of them live on higher floors. When they leave, they all take the elevator down. So even if the elevator moves up and down the same number of times, you're far more likely to share it with someone going down. To you, it feels like the elevator is always heading down. But from the elevator's point of view, it's just doing its job. This isn't just about elevators. This is about how we see the world. It happens when you think traffic is always worse in the lane you're in, or that your friends always seem busier than you are, or that the internet is full of people who disagree with you. It's not necessarily true. It's just the paradox of where you're standing. So the next time you wait for an elevator and it's full of people going down, ask yourself, is it the world that's unbalanced? Or are you just catching the universe mid-pattern? And if that's true, How many of our so-called truths are really just illusions of where we happen to be standing? Nothing makes sense, and maybe that's the point. So, after all the thought loops, contradictions, and impossibilities, after all the paradoxes that shattered reason, what are we left with? A universe that's deeply logical, but also deeply strange. A world where the closer you look for certainty, the more it crumbles into questions. We went searching for clarity, and instead found a mirror, reflecting back every flaw in how we think, how we choose, how we even exist. Because maybe paradoxes aren't just bugs in the system. Maybe they're messages, reminders that not everything can be known, that not every question has an answer, that somewhere between logic and mystery is where truth actually hides. And maybe, just maybe, the fact that we can even ask these questions is the strangest paradox of all. So now I'll leave you with one final thought. If you watched this video and it changed the way you think, then who exactly was you before it began? If your brain feels twisted in all the right ways, drop your favorite paradox in the comments, and let's keep the mystery alive. Because in the end, the deeper you go, the weirder it gets.